Yesterday we looked at Michelson's experiment, and Michelson's experiment provided us with a way of measuring the speed of light. We have an applet up on the board that we showed you yesterday. We're going to show you a slightly different version of it today. This one's going to show us light pulses, and this one should show us, I think, a little bit better the whole idea of 1/8 of a revolution during the time that it takes the light to travel that distance, that return distance from the rotating mirror to the flat mirror and then back again. We're on one hill over here on the left-hand side. This is another hill over here that's 35 kilometers away. Although you got to be careful about that distance because every question that you see may have a slightly different distance. I've seen questions that have been 30 kilometers or 40 kilometers or whatever. Okay, the standard distance is 35. But be alert for something other than 35 kilometers. You have an 8-sided mirror that can rotate. Okay, be alert for that as well. Okay, I've seen questions where we've had a 12-sided mirror or a 6-sided mirror. Okay, if you've got a 12 or a 6-sided mirror, then obviously that changes the question ever so slightly. We've got a flat mirror on the other side. The light goes down here. The light comes right here. It reflects off of that surface that you see it hitting there, comes down here, reflects off of this mirror, comes back, and then gets detected by this observer right here, as illustrated by that eye. Let's say this 8-sided mirror is stationary right now. It's not rotating right now. If that's the case, then there's no issue whatsoever with this light striking that side of the mirror right here, bouncing down here, hitting that, bouncing back, hitting that, and then striking the eye there, striking the observer there and being detected. Okay, it does that. But it doesn't help us in this situation because we have no way of measuring time. The whole idea of rotating this mirror is to provide us with a mechanical way of measuring time that doesn't rely on reaction time, as in Galileo's experiment. We eliminate reaction time with this experiment if we can measure time with this mechanically spinning 8-sided mirror. So, let's erase this beam of light, and let's start spinning this thing. When we start spinning this thing at a slow rate of speed, the light is still going to reflect off of one side of the mirror or the other, but it's not going to reflect to where we want it to reflect. It's going to reflect not to a random place, but it's going to seem like a random place. As the side of this mirror is now at a different angle, then the angle of reflection off of this mirror will also be at a different angle. It's not going to be detected by the observer. So as I turn the frequency up a little bit, it's not detected by the observer. The light pulse disappears. The observer doesn't see it anymore. As I turn it up a little bit more, still can't see it. As I turn it up a little bit more, still can't see it. As I turn it up a little bit more, all of a sudden the observer sees it again. Why is that the case? Well, in order for the observer to see it, one side of this 8-sided mirror has to be in a very particular place to cause the reflection to go in that particular place, to cause it to go where the observer is. It has to have made 1/8 or 2/8 or 3/8 or so on of a revolution during the time that it took the light to go from here to here. Now I'm going to go step by step through this and show you exactly why that's the case. Okay, we've got a flash of light here. Okay, this flash of light has just reflected off of that surface. Okay, off of surface number 1, we'll call it, the one with the little red line there. You can see that the mirror is also rotating during this time. Okay, this pulse of light is going from that one side of the mirror, that red side of the mirror, going down to the second mirror on the second hill, reflecting, coming back. If it hits that rotating mirror at the right angle to be detected here, then how far has that red side of the mirror rotated? How far has it gone? It's gone 1/8 of a revolution. It's gone 1/8 of the way around. So now we know that the time that it took for the light to travel this distance and then back again this distance was the same as the time that it took this mirror to make 1/8 of revolution. Now, if I had spun this mirror faster and made 2/8 or 3/8 or 4/8 of revolution, we would have gotten the exact same effect. We still would have seen this light reflecting off of the right place and therefore getting detected by the observer. But the way we did this is we started it at rest, we turned up the frequency just a little bit, light disappeared, and then we stopped turning the frequency up when the right light reappeared at the observer. So we've got the slowest frequency that it can go at in order to make this happen, in order to be observed by the observer. That means that it's got to be the time for 1/8 of revolution. Now, if we know the frequency of this, okay, let's say the frequency is 550 hertz, and I'm just making that number up right now. Usually it's somewhere in the range of 500 to 600 hertz. Okay, the frequency of rotation of this mirror, 550 hertz. Let's say that we know the distance that the light travels there and back, 35 kilometers there, 35 kilometers back. The distance that it travels is 70,000 meters. We're able to determine from that, literally just from that, the speed of light. We know that every time we see one of these questions, we write down two equations. V equals d over t, because the light's traveling at a constant speed, and we write down t is equal to 1 over f. The period is equal to 1 over the frequency. This time, this big T stands for the period, the time for one revolution. This little t stands for the time for 1/8 of a revolution, or if the mirror has 16 sides, it would be 1/16 of a revolution. Big T and little t, two different times. Also remember that when you plug your numbers in here, you're going to find one of those t's. The first thing you're going to get is either big T or it's going to be little t. It's not going to be the one you want. If you need little t to solve for V, then what you're going to get first is big T. If you need big T to solve for F, then what you're going to get first is little t. Let's plug our numbers in, get whatever t comes out, and then let's use that to find what we want to find. We don't know the speed. We do know the distance. It's 70,000 meters. We don't know little t. Let's go over to the other equation. Big T is equal to 1 over f. That's 1 over 550 hertz. We get a number for that. Doesn't really matter what it is right now. We get a number for that. That's the time for one revolution. But remember what I said. That's not the time we want. If we get big T, then we want little t. How am I going to get the time for 1/8 of a revolution if I already have the time for one revolution? Divide it by 8. Okay, we divide it by 8 to get the time for 1/8 of a revolution, which we turn around and plug back into here to solve for speed. Now, if we were solving for frequency, we would have first gotten little t, the time for 1/8 of a revolution. We would have had to do something with that to get the time for one revolution. In fact, we would have had to multiply that by 8 to get the time for one revolution. So always write down these two equations. Always plug your numbers in. Always get one of the times. Always either multiply it by 8 or divide it by 8 to get the other time. And then plug it back into the other equation to get what you're looking for. We had 3 questions for homework last night, 1, 2, and 3 on page 650. Any issues with any of those questions, please? None, really? Good, excellent. All right, if you're that good at these questions, then it won't be an issue at all to do for homework this weekend, worksheet number, I believe it's number 14. Worksheet number 14. The good news is there's only 3 questions on that page on worksheet number 14. I want to do one more example with you, though. This one isn't a Michelson experiment. This is just a general speed of light question, just to kind of refresh your memory from Physics 20, how wave speed calculations work. This one says the distance from Calgary to Regina is 800 kilometers. How long does it take light to travel from Calgary to Regina? If the wavelength of the light is 600 nanometers, what's its frequency? Should say the distance from Calgary to Regina, not from. 800 kilometers, that's my distance. We should probably circle that kilometers because we want to convert that to meters, right? We always want to go meters. How long does it take? Okay, we're looking for time. We've got the wavelength here, but we should circle that as well because that's in nanometers and we want to be in meters. We also want to find the frequency here. When you're doing a straightforward speed of light calculation, speed of any kind of EMR, by the way, this could be visible light, but it also could be a gamma ray or an X-ray or a microwave as well. It doesn't matter. Any kind of light has a speed of 3 times 10 to the 8 meters per second in a vacuum or in air. Now that speed decreases as you go through water or as you go through glass or plastic or whatever, but presumably we're going to be in air here. Most calculations you do with the speed of light, you're going to be in air or a vacuum. So the speed will be 3 times 10 to the 8. The distance is 800 kilometers. We want to find the time. Let's just use the equation v equals d over t. Rearrange it to get t. I get d over v. That's 800,000 meters divided by 3 times 10 to the 8. What do you get for that, Carson? Times 10 to the negative 12? Yeah, I don't think it's 1.33 either, actually. 2 point something. So 2.67 times 10 to the negative 3. You might have divided the wrong one, the wrong way around, Carson. 3 over 8 instead of 8 over 3. 2.67 times 10 to the negative 3 seconds. So light takes only 0.00267 seconds to go from Calgary to Regina. Back to Galileo's experiment for a second. He had his hills 1 kilometer apart. Right? This is 800 kilometers. The time that he would have had to start and stop the stopwatch would have been ridiculously small, like 1/800th of that time that we have right there. All right, we want to find the frequency of the EMR as well. The other equation that we can use besides v equals d over t is, of course, that wave equation that we learned in Physics 20, v equals f times lambda. F is equal to v over lambda. We did this on our quiz today, right? Our speed is 3 times 10 to the 8. And our wavelength is 600 times 10 to the minus 9. That should give us 5.0 times 10 to the 14. You weren't asked this question, but you could be on a test or a quiz. What kind of EMR is that? It's visible light, because it falls within that range of 4 to 7.5 times 10 to the 14. That's not too bad, is it? Okay, we've got about 10 minutes left in class here. Here's what you're going to do for the last 10 minutes. Worksheet number 14, which is on Mickelson's experiment here. 3 questions on that page. In addition, you're also going to do worksheet number 15 that I'm about to hand out to you, which are questions on this. They all should go fairly quickly for us. So as much as we have 2 worksheets, you could very easily be done one of them before the end of class here today. Okay, that's it for today. We'll check those over on Monday, and then we'll move on from there.